Hello, I'm Dr. Kanade. Today we will see a problem of generation of square wave using timer 0 in PIC18458, and in particular we are going to see embedded C program for this. We will write a C program for generation of the square wave. Okay, some of these things we have already seen earlier, but for the sake of completeness of this lecture, I'm going to cover the complete procedure or the complete process of writing this program, in fact solving this problem. Okay, so the first thing when we want to generate a square wave is there are certain steps that we will have to follow. Okay, because we are going to use timer 0, means we will have to program the timer 0 or configure the timer 0 for this particular task. In fact, when we say square wave, means we want a digital wave, a square wave having 50% duty cycle, means 50% of the time it will be on and 50% of the time it will be off, right? This is how the square wave works. Okay, so these are the steps to program timer 0. The first and foremost, as I said, we have to configure the timer. That is done by loading the value in T0con. Now, what value to load this? In what value to load in this T0con register? It is decided based on the calculations, based on the requirement, based on the setting of the hardware, like what is the crystal frequency that we have connected to the microcontroller. Based on these things, we have to calculate the value, and that we load in T0con. Okay, then we have to if I'm going to generate that that square wave on RB0 pin, for example, then I have to first set that pin as output. This is done by using the TRIS register bit, right? We have seen this in IO port programming, that if we want to set a particular pin of a port as output, then we have to set the value of that particular bit in the TRIS register as 0. If we want to make it an input pin, then we have to set that value as 1. Okay, then we are going to load initial count values, and those are also calculated values, again based on the crystal frequency and our required value of delay, required amount of delay. And that is done by, if we have 8-bit, if we are using the timer 0 in 8-bit mode, then we are going to need 8-bit value only, and that we will load in TMR0L. If we are using 16-bit timer, then we will load the values in TMR0H and TMR0L, right? H will hold the higher byte and L will hold the lower byte. Then we will clear the TMR0IF flag. This is to ensure that what is this flag, by the way? TMR0IF is the timer 0 interrupt flag, which indicates the timer has overflown. In order to ensure that we do not have any residual value of this interrupt flag, we are going to clear it, so that whenever it gets set, it will indicate that the timer 0 has actually overflown. Okay, then we will perform the desired operation. Now, for example, in this case, we want to generate a square wave. So wave means there will be on off switching. So here at this particular step, we will perform the toggling operation, toggling of the bit. That's it. That is the only operation that we are going to perform in this particular case, because we are only interested in generating a square wave. However, however, we can have any set of operations that we can perform, which we are going to perform repeatedly after certain amount of delay. Okay, for example, copying some data from one port to another, or from one register to another register. These kind of operations can also be performed at this particular step. Okay, Then we will run the timer by setting the TMR0 on bit as 1. TMR0 on bit. This bit is again in T0 con register. We have to just make it 1. When we make it 1, the timer starts its timing, right? Then we will keep on checking the timer 0 flag, TMR0 IF, and see here we have made it 0. So whenever we will keep on checking, and when it becomes 1, it means that the timer 0 has overflown. Means the amount of pulses that we have calculated here, the amount of pulses that we have calculated in the and told the timer to measure in step 3 have been completed when this overflow happens, right? So based on that, we now become sure that the delay is complete. The amount of delay that we have calculated has now completed. Okay, so we will stop the timer and we will go back to step 3, and from there we will again initiate the same process again and again, and we'll keep on running this, right? So you can see here we are going to need 2 loops. This one loop that is visible clearly from 9 to 3, it is going up like this, and second loop is here basically in this single statement number 7, keep checking timer 0 flag. In this statement itself we will need one additional loop. Okay, as far as the calculations are concerned, if we want to generate 1 hertz pulse, okay, and crystal frequency is XTL equal to 20 megahertz, then as we know already now that the instruction clock frequency is the XTL divided by 4, that is 5 megahertz in this case, and the instruction clock period will be 0.2 microseconds. However, how much delay do we want? We want 1 hertz pulse, means 500 millisecond on and 500 milliseconds off. Means how many pulses of 0.2 microsecond duration? That is 5 lakhs divided by 0.2 is equal to 25 lakhs pulses will be required to be measured, but it is not possible using timer 0 simply, because maximum pulses that timer 0 can measure even in the 16-bit mode is FFFF plus 1, that is in decimal numbers it becomes 65536, right? Maximum these many pulses can be measured by the timer 0 in 16-bit mode without using prescaler, right? But we want these many pulses in this setting, so this is not possible. Therefore we will use prescaler, and from our calculations we can say that now we need 1:64 prescaler, so that the timer clock frequency gets again divided by 64. Here it was, we had found out that timer clock frequency, basic timer clock frequency or the instruction clock frequency is 5 megahertz. When we use prescaler, it again gets divided by 64. So the frequency is this much, and the timer clock period is now 12.8 microseconds, right? So now again we will calculate how many pulses are required, how many pulses each of 12.8 microsecond. So we will again divide the same number, 500 millisecond or 5 lakhs microseconds divided by 12.8 is equal to 39063 pulses need to be measured, need to be counted. Each pulse is of 12.8 microseconds, right? So how to program this? We need to subtract this particular number 39063 from the maximum number of pulses, that is 65536. So we will subtract this particular number from the total number 65536, and the result is what we get here. It is 26473. I am talking in decimal numbers for the moment, right? 65536 is also decimal. 39063 is also in decimal. The subtraction is 26473. This is also in decimal. Just for writing the program to make it simpler, because we are going to write this number in HL pair, TMR0H, TMR0L. That's why we need hexadecimal value. So we convert this. So it comes out to be 6769 hexadecimal. This value will be loaded in timer. Okay. This is one important calculation. The second important calculation is of the T0 con, and it is based on the prescaler what we have selected on the last slide. The prescaler what we have selected is 1:64. So for that, the corresponding values of these 3 bits are 101, T0 PS2, T0 PS1, T0 PS0, like this. Okay, the values are 101. This is based on the configuration given in the PIC 18F datasheet. This is pre-decided that if you set these 3-bit values as 101, then you will select prescaler 1:64, provided PSA is also 0. PSA 0 means the prescaler is assigned, means this prescaler will be used if PSA is 0. We are using timer mode, so T0CS equal to 0, and in timer mode T0SE has no meaning because there is no question of source edge. This T0SE is whenever there is an external clock pulse being used with the timer 0, but here we are using internal clock pulse, so there is no question of source edge. T0 8-bit, again it is 0 because our timer is, we are using in 16-bit mode. If we want to use in 8-bit mode, then we have to make it 1, right? And as I said, TMR 0 on bit should be 0 at the time of starting the program. We will make it 1 as you saw in the steps that I had just discussed earlier. So that bit also is 0. So therefore T0 con is now 00000101, or in hexadecimal it is 0x05. Okay, so these are the important calculations that we have to perform, and then we write our this is the summary of the calculations. T0 con will be 0x05, TMR0H will be 0x67, and TMR0L will be 0x69. Now we are going to use these calculated values in the steps that we have just discussed, and we will convert those steps into our program. Okay, we have seen this assembly language program already. Okay, this is the same conversion of the same steps into assembly language program. We have already seen this, so I am not going to repeat this now. We will jump to writing our C program now. Okay, meanwhile you can keep a screenshot of this with you if you want. Anyway, this is available to you also. So to start with the embedded C program, what we will do, I will keep these steps on this side. These are the steps that we just saw. We are going to convert these steps one by one. Okay. As we are talking about C program, the first line of the C program is, as usual, even with the standard C or with embedded C, it has to be the include line, and we are including the P18F458.h, this header file. This header file is what? This is the header file corresponding to our microcontroller. This is provided by the microchip, the manufacturer of P18F458, right? Okay, then we will start the main function. We will say void main void, because we are not returning anything by this main function, as well as the main function is not accepting any argument. Okay. Now, the first step. What was the first step? Here, load the timer. Configure the timer load value in T0 con, right? So the value that we have just calculated for T0 con is 0x05. So we have loaded that value, T0 con equal to 0x05. Second thing, set RB0 as output. Why RB0? Because we are generating the 1 Hz pulse on RB0, right? RB0 means bit 0 of the port B, right? Bit 0 of the port B. So how to do this? To set RB0 as output, we need to set the corresponding bit of the trace register as 0. Means trace B registers 0 bit as 0. So that can be accessed using this particular syntax. Remember this syntax forever. There will be the name of the registers first, and the name of the register, as we have been knowing since we have been talking about IO port programming, that it is TRISB is the register name. However, we are not setting the whole port as output port. We are only setting one single bit of that port as output pin. So for that, we have to use the bits configuration. So what is that? TRISB bits dot TRISB0. TRISB0 is the bit. The syntax of this particular way of accessing bits in the PIC18F is name of the register followed by bits without any space. Name of register is in capital letters, bits is in small letters, dot followed by the name of the bit. Okay, that is how we can access any bit in this microcontroller, and this value 0 corresponds to the setting of output. Okay, so using this particular statement, our RB0 pin will be configured as output pin. Means we can send a value, a 0 or 1 value to the RB0 pin. Okay, then we are you see here I had drawn a loop like this, right? I had drawn a loop like this because we are going to repeat this, loading the initial count values. So we will start our loop here while 1. Now while 1 stands for what? 1 stands for infinite loop, right? Because we are going to run this continuously. This particular loop from 3 to 9 we are going to run continuously. Okay, so while 1 is the way of saying that this is an infinitely running loop, and then we are loading these values. Now as per our calculations, we are going to use 16-bit timer. TMR0H is 0x67 and TMR0L is 0x69, right? As per our calculations shown on some previous slides. So TMR0H is 0x67, TMR0L is 0x69. We are just assigning these values. So this is what we mean by loading the initial count values into TMR0H and L. Remember that this value, and this value, these three values are calculated based on the crystal frequency and the required frequency. Crystal frequency is 20 megahertz and required frequency is 1 hertz. Based on these two settings, based on these two given data, we have calculated these three values. Okay, now the next step is what? Clear TMR0 IF flag. That again we will use this kind of syntax. Okay, so for that we must know where this TMR0 IF flag is. TMR0 IF flag is in which register? Do you remember? It is in the INT-con register, right? So again using the same kind of syntax, INT-con bits. INT-con is the register name, bits because we are accessing a single bit, dot TMR0IF. TMR0IF is the name of the bit, right? And we are making it 0, clearing the flag, right? Now perform the desired operation. What is the operation that we want? We want pulse generation. Means we want transition on the RB0 pin. Transition means from 0 to 1 or from 1 to 0. This is toggling transition. This is just, or you can say complementing the bit, and that's what I'm going to use here. Port B bits dot RB0. This is tilde equals port B bits dot RB0. What I have done, just complemented this bit, or made negative of complemented this particular bit. Not operation we have used here, right? So if this bit was initially 1, it will now become 0. If this bit was initially 0, it will now become 1. Please note that here the register is port B. Here the register was tris B. Why is it so? Because here we are just setting that particular pin as output pin, and for that we have to use the tris register. And when we are actually sending some value, when we are actually assigning some value to a particular pin, at that time we are going to use the port register, right? Port register. Here we are actually sending the value to the port B register. Okay, in fact only to RB0 bit, RB0 pin to be precise. Okay, so this is the operation that we wanted, that we want to toggle the RB0 value from 0 to 1 or from 1 to 0. Okay, now we will run the timer by setting TMR0 on as 1. How to do that? Again, using the same kind of structure, same like this. So for that, again we need to know where this TMR0 on bit is. It is in what? T0 con. So using the same syntax, T0 con bits dot TMR0 on is equal to 1, right? We must know that this TMR0 on bit is in T0 con register. So T0 con bits dot TMR0 on equal to 1. Now the most different part, I would say, is the step 7, to keep checking the timer 0 flag TMR0 IF. Now what does it mean? We want to use a condition that this particular flag, whenever it becomes 1, we have to stop the timer, right? Whenever this flag becomes 1, we have to stop the timer. Unless and as long as that flag is 0, we have to do nothing. Remember my words, note down. As long as TMR0 IF flag is 0, do nothing. And how to implement that? You have different ways. Of course, you can use some of your own logic, but the simplest and shortest way is by using this. See what I have written here? While inticon bits dot TMR0 IF double equals 0. This double equal sign means comparison sign. This is a, is it equal? This is standard C syntax, right? Standard C comparison operation. If this flag and this value is equal, what will happen? It means that this condition is true, right? And until that, when this condition is true, what happens? While loop gets executed, means we remain in while loop. But however, there is a semicolon at the end of this statement. Please note down this semicolon at the end of this particular while loop. So what will happen here is, as long as this condition is true, the compiler will or the program will remain here only, on this statement only. As long as this condition is true, the program will remain at this particular statement only, right? Because while condition is true, it keeps on executing the while loop. When this particular condition becomes false, means when this becomes 1, when this TMR0 IF flag becomes 1, the condition will become false, and that's when it will exit the for loop, exit the while loop and go to the next statement. And that next statement is as here written, step 8, we will stop the timer. So again here T0 con bits dot TMR0 on equal to 0. When we make the timer TMR0 on bit at 0, timer will stop. When we make it 1, here as here, the timer starts, right? Now the next step is we have to go back to step 3, means we have to go at the beginning of the while loop. That's it. So our while loop has now ended, right? Now what is just remaining? What remains now? We have to just complete the main function. That's it. And this is how our program is now complete. You can see here, when we completed this while loop here, when we put a curly brace, closing curly brace here, it means that this is now the block of statements under this while loop. And this, since the condition here is 1, while 1 means this block will keep on executing continuously, right? It will keep on executing continuously infinitely. And what is happening every time? What is happening every time the block executes? The timer starts from these values and the bit gets complemented, or from 1 to 0, 0 to 1, it gets on that transition. So ultimately what is happening is we are starting from these values, means totally we are having 500 millisecond delay, and that delay we are actually inserting at this location. See, starting of the timer, here we are starting the timer and here we are stopping the timer. From starting the timer to stopping the timer, we are having 500 millisecond delay. And for that, after each of that delay, what is happening? The port B bit RB0 is getting inverted. So what ultimately we will achieve is port B bit RB0 will remain 0 for 500 millisecond and remain 1 for another 500 millisecond, and like this it will keep on running like this. Every time we have 500 millisecond. Here also we will have 500 millisecond, right? So every on as well as off state will have 500 millisecond, and that is how we get totally 1 second here. This is 1 second time period, right? 1 second full time period, and 1 second time period means what? 1 hertz pulse, right? Frequency is equal to what? 1 by T. T here is 1 second, so F is 1 hertz. So this is how we are generating 1 hertz pulse, right? We are generating 1 hertz pulse on RB0, right? So this is how we write this complete program. I hope it is clear to everyone. If you have questions, you can ask. Okay.